Good day, and thank you for joining us today. We have another amazing show and a terrific guest lined up for you. Today, we're looking at how space based weather intelligence and environmental monitoring can help us get a lot smarter about how we are looking at weather events. Welcome to the Tech and Space Leaders Show, where we learn lessons from leaders of the next frontier. I am your host, Lisa Dreher, and I'm really excited to introduce our guest for today, Drew LePage. He is the Chief Scientist at Tropical Weather Analytics. Welcome to the show.
Glad to be here. Thank you for having me.
Yeah, thank you for being here, Drew. Perhaps we can start by having you give a little bit of background on yourself and Tropical Weather Analytics.
As was just said, I'm the chief scientist at Tropical Weather Analytics. We're a small startup company located in the Boston area. By training, I'm a physicist, and for the past 40 something years, I've been of my career specializing in optical instrumentation as well as things along the lines of digital image processing, digital data processing, computer vision, other types of applications. And for the past 30 something years, I have been primarily focused on atmospheric remote sensing using data from ground-based, air-based, and space-based platforms to characterize various properties of the atmosphere, the clouds, aerosols, and turn that into useful data products for other scientists to be using further downstream. So, in addition to that as well, I have for the past 36 years, I've been having a side gig, as it were, as a freelance writer, specializing in space-related topics, especially the history of spaceflight, which turns out to be very useful in my line of work to see how things were done in the past. And it's interesting how some of the solutions of the past end up being solutions for today for various types of problem solving.
Right. How is the work that Tropical Weather Analytics is doing different from maybe the way we have done weather monitoring traditionally?
Well, the for our particular satellite constellation, which we have called the Hurricane Hunter satellite, which is a bit of a nomer. We started off looking specifically at hurricanes, and then excuse me, and then broadened it to be able to look at a whole range of weather phenomena, severe weather, even just day-to-day weather, even when it's not all that severe. What we are doing that's different is we're flying our satellites in pairs. Most satellites, weather satellites today, they're these gigantic platforms that literally weigh tons, cost hundreds of millions of dollars to build and to launch and to operate. And they do their jobs very, very well, but they're trying to be a platform to try to do everything for everybody. We are focusing in on just a very specific set of topics, and we're doing it in a different way with much smaller satellites. The Hurricane Hunter satellites, at least these first incarnation, the initial constellation, which are being built by our strategic partner, Phantom Space, located in Phoenix, Arizona. They're doing not only the building of the satellites, our payloads, launching and operating. And we operate these satellites that are literally the size of a couple of shoe boxes. So they're very, very small, cost just a couple of $1 million a pop to build and get up there. And unlike other satellites where we just have a single satellite doing its thing, we are flying our satellites in pairs so that as we go along across the Earth, we have two satellites looking at different directions. And just like we have two eyes to do stereo so that we can tell whether something's really close or really far away, we use computer vision techniques to take those images and to do a stereoscopic analysis so that we measure very accurately the altitudes of those clouds. And by taking a series of observations over time, over the course of about a minute, we're able to derive the motions of those clouds. And we can use the motions of the clouds as basically a surrogate to determine what the winds are at those altitudes of the clouds. Now, for the past decade or so, NOAA, with their geosynchronous satellites and I think also their polar orbiting satellites, they do something similar where what they do is they monitor the motions of the clouds and other atmospheric features over time. But they only have a single satellite looking down and making these observations. So what happens is they have to use a different technique in order to determine the altitudes. And it's basically a sounding technique. They make observations in a whole range of different bands in the infrared and other wavelengths to basically divide up the atmosphere into a bunch of little bins to determine, okay, what's the altitude? But that's a very, well, comparatively, a very inaccurate way of measuring those altitudes. At best, close down to the ground, they're measuring the altitudes to an accuracy of maybe hundreds of meters or so, and up towards the top of the troposphere, where all the weather takes place in the atmosphere, about 10 to 15 kilometers up, that uncertainty ends up being literally kilometer or kilometers. So it's very, very, very inaccurate as far as the altitude of the clouds. Using our technique with our purpose-built pairs of satellites doing stereoscopic observations, we're able to determine the altitudes of those clouds to about 100-meter accuracy anywhere inside of the troposphere. So basically, we combine our very precisely geolocated features in the cloud field and track those over time, and the altitudes and how they change over time. We're able to derive not only the horizontal winds, but uniquely the vertical winds. So that's really important in certain parts of weather, especially severe weather, where you get lots of convection that then produces these storm clouds that lift up high into the atmosphere and are associated with really, hard downpours, severe weather, tornadoes, those types of things. So we're able to make not only the horizontal measurements very accurately over a wide area, but also the vertical wind measurements.
Wow, amazing. So where are you in the development of the constellation at this point?
Well, as I said, we do have a strategic partner who is already already developing the satellites and build the satellites and launch them and operate them, as well as develop the camera payload. The camera that we're doing in order to keep this thing inexpensive, at least initially, and quicken the development and limit the development costs. We're just doing visible band cameras, the cameras that are available today, miniaturized camera packages and whatnot. They are really, really, really huge arrays, very, very inexpensive comparatively. So we're limited to doing just daytime observations. So that is one limitation compared to what's done with other satellites, which have an infrared capability.
Understood. Okay. So in the beginning, you kind of mentioned that you were originally just looking at hurricanes. What all are you looking at now?
All types of weather. Like I said, initially we were looking just at hurricanes. This was part of an effort that actually goes back 30 some odd years ago. There was a Defense Department project that my team and I were involved in at the time, that we were doing 3D observations of atmospheric phenomena in order to understand what the Earth backgrounds would look like at various wavelengths in order to develop better early warning missile systems, which are currently being used to maybe a little bit too often lately to actually look at these ballistic missiles that are coming to from or to targets that are of interest to us. So about a decade ago, we resurrected some of that technology that we had developed way back around the turn of the century. And that sounds odd saying the turn of the century now, but back at the turn of the century, to do a commercial application to initially look at hurricanes. There are physics-based techniques to basically look at very precisely what the altitudes of the clouds are and the cloud top temperatures versus what the temperatures are at the surface of the ocean, to then estimate how strong is a hurricane. During the course of a precursor project that we flew on the International Space Station between 2014 and 2019, it turned out the way we were taking our data in order to do these types of observations of cloud top altitudes very accurately, we could also determine the winds. And we quickly found out that there are these gaping holes in how winds are determined, because winds are very important, or arguably one of the most important aspects of weather. The winds are what drives weather systems around, as well as weather systems like hurricanes, for example, creating their own winds and whatnot. So we quickly went from looking at just the eyes of hurricanes with an orbiting instrument to this very wide field of view instrument that would then look down on the Earth below. We still kept the Hurricane Hunter satellite, even though we're now doing something much more than just hunting for hurricanes. We're actually looking at winds from of all types of weather systems, and that wind data is vital for initializing various types of computer models to do weather forecasts. Nowadays we have winds aloft are measured from a range of different methods. There's these weather balloons that are sent up typically twice a day worldwide, but they're highly scattered across the globe, and you have to interpolate your data over hundreds of kilometers sometimes. There's also different types of radars that can be used to determine the altitude, determine the winds at altitude by tracking aerosols, cloud features, things like that. But again, those have very limited range. There are aircraft, a lot of commercial aircraft are part of a larger international program where as they fly along, they are collecting data on winds, temperatures, humidity, things like that. But again, those are mainly concentrated along the air routes between various locations across the globe. And also, aircraft tend to avoid really bad weather, so you can't get observations of what's going on in there. Now, about a decade ago, NOAA, with their GOES weather satellites, these are the weather satellites that are in geosynchronous orbit, they introduced these atmospheric motion vectors, a technique to basically track cloud features over time, atmospheric features over time, to infer what the winds are. But the resolution, the gridding on that data product is literally tens of kilometers. And as I explained earlier, they're using a sounding method that is only good to at best hundreds of meters to kilometers as far as the altitude determination. So combining our 100-meter class imagery with the very accurate geolocation of features and the altitudes of those features, we're able to determine the winds as accurately, if not more accurately, than it's currently done with GOES. And in addition to that, we instead of having this gridding of tens of kilometers, we're able to do this on sub-kilometer scale, so much higher resolution than is typically available today over wide areas of the globe.
Wow, that's amazing. So are there other variables? I mean, it sounds like the wind is really an important factor. Are there other variables that are really challenging to capture?
Oh yeah, there's a whole array of instruments that are on various types of weather satellites, including some small commercial weather satellites. We're hardly Tropical Weather Analytics is hardly the first one to provide weather data commercially from satellites. But there are other satellite systems up there that do soundings of the atmosphere, so you actually get a profile of how temperature, humidity changes with altitude. That's an important piece of information. That's not what we're measuring, at least not with this current generation of satellites. So there's a range of information, but one of these important inputs is what they call 3D winds. What is going on with the winds? And with our system, our constellation, where we can revisit any given point on the Earth as frequently as about an hour and a half, we're able to provide very high resolution initialized conditions. And to be honest, I think we have discovered over the past couple of years with our interactions with the rest of the science community that the data that we're providing has too high of a resolution to be handled by the current physics-based models that are used for numerical weather predictions. So it turns out that AI type weather prediction models are actually ideally suited to input our data at its native resolution. And there are also other applications as far as the other data that we create. For instance, we are able to measure the cloud altitudes very accurately, and that can be used in combination with other types of sounding methods. For example, to provide hard boundary conditions of what is going on at a very specific altitude, so they get much more accurate results of what's going on in the clear air above the cloud deck that we're sensing. So in that regard, we indirectly help these other types of instruments that are trying to also do these remote sensing observations that are vital to provide inputs into weather forecasting models.
Wow, amazing. So when you look at improved forecasting, how does this really help with preparedness for extreme weather events?
Well, for all types of extreme weather, whether it be like I said, we initially started with hurricanes, so we have done a lot of work with hurricanes and whatnot. But there's the need to be able to predict, like in the case of a hurricane, and the same applies for other extreme weather events. Where is it going, and how is it going to develop? And that depends on the winds. For example, hurricanes. They get more and more powerful over time. The altitudes of their clouds tend to get higher and higher, but eventually they reach a point that can only get just so powerful because the winds are now going in a different direction at that higher altitude and shear off the tops of the clouds, limiting how much more powerful that hurricane can get. So our system will provide information to help tell you, okay, this is where you have the wind shear. Also the driving winds. How are the winds at various altitudes? How are they moving so that they're moving the severe weather or just regular everyday weather? How those systems are going to be driven? And it's really interesting because I know that I live here. I live in New England, and of course we have really odd weather in New England. And one of the things I found talking to other meteorologists, area meteorologists, is that very frequently, even in the winter, we don't get really good wind data just off the East Coast, which is really necessary when you've got these big systems working their way up the coast. What are the winds? Where are they going to go? How are they going to affect the evolution of these storm systems, which eventually come up the coast, give us our classic New England nor'easters, which dump a foot or two of snow on us. So there's a wide range of applications that our data has to help improve weather forecasting in general, where we're making our observations.
Yeah, you make me curious just in some of the things that you're talking about. Have you gotten interest from other industries like the maritime industry or?
Oh, absolutely. Oh, yeah, because that's one of our jobs, since we're a commercial venture. We're not government funded, although the government can be, or hopefully at some point in time will be a potential customer for our data products. We've looked at a number of industries, and obviously weather drives a lot of things having to do with transportation, airlines, shipping the cruise industry. They literally have their own weather departments available to figure out, okay, where's the bad weather? Where do we have to move our ships? Okay, here are our, here are our stops. Here are the limitations on ports we can go to or what we can. So it helps. Literally, we've done some studies and whatnot, and even if a shipping company is able to save 1% by slightly redirecting a ship or a plane or some other cargo conveyance, shift the path it's taking and save just 1%. That is a huge amount of money to a shipping company, being able to save just that 1% by getting a more accurate forecast of what's going to happen and how things are going to develop.
Right. How do you also see this, I guess, supporting things like agriculture and infrastructure, supply chains, all of those types of things?
Well, in the case of supply chains, a big hunk of supply chains is the transportation, which I just was talking about. But also there's use for this data as far as agriculture is concerned. Because again, farmers need to know, when is it going to rain? When do I have to go on and put on my sprinklers or take either water out of my pond or take increasingly scarce water out of a regional aquifer to do things? And if they get better weather intelligence as to what's going to happen with the weather, what's going to be happening with the cloud cover, when that ends up saving them money in the end, and being able to better plan when do I water plants, when do I apply various chemicals, fertilizers, and whatnot, and also when do I harvest my crops again, to maximize their return. So there's a range of industries that end up taking advantage of this up-to-date weather intelligence, and we are providing, at least as far as initial conditions on winds, we're providing this kind of high-def version of weather information, which is vital, especially when you're talking about hyperlocal, or what we call hyperlocal, very localized weather forecasting. What's going to happen in not only in, my particular county in Kansas, but my particular little corner of some county in Kansas. And you need that higher resolution, high revisit rate data in order to input into models and make the predictions that are necessary to help them out.
Oh, wow, amazing. Okay, so what is your time scale? What are we looking at in terms of getting your constellation launched, and when do you expect you might be online?
Well, as it stands right now, we're looking at probably 2028 to get the first pair of satellites into orbit, the Hurricane Hunter satellites. We're currently working with Phantom, and they are in the process of working on their own satellite constellations for commercial purposes, and for basically space-based cloud data processing and movement of data to quickly to other locations. In any case, they're going to be launching, hopefully later next year, a prototype satellite, or a pair of prototype satellites that will also carry some of the systems that we require for our Hurricane Hunter satellites, the cameras, star cameras, in order to determine very accurately the orientation of the satellite as the imagery is being taken. So hopefully they'll be able to start returning some data maybe towards the end of next year that we can actually use before we even get the first Hurricane Hunter satellites up. After that, it's really dependent on how well we raise, how well we're able to raise money, because we are a commercial venture. We're not relying on the federal government for funding or anything like that. So we're doing, venture capital and so on to raise the money that we need to do what we do. It is our hope that within a half a year of getting up that first initial satellite, pair of satellites, that we'll be able to launch a batch of several pairs of satellites, like maybe 6 months or so later, and then another 6 months or so after that, get the next batch of satellites up, get them all placed in the proper orbital plane so that we can make these observations every hour and a quarter from about 7 o'clock in the morning till about 5 o'clock late in the afternoon or so, and start producing this literally a torrent of data that would cover much of the globe.
Wow, fantastic. So if someone wanted to learn more about tropical weather analytics, what should they do?
Well, the easiest thing to do is to go to our website, www.weathersats.com. We have a lot of information about our satellites, how we're going to be making our observations, examples of business cases of where these data are actually going to help things, as well as a whole bunch of blog posts where myself and other members of the team take deep dives into various aspects of what we're doing and how it helps various industries and whatnot. And there are also a whole series of articles in there that where we've gone back to our precursor project that we had flown on the International Space Station that was funded by CASIS, which is the government organization that runs the American lab in on the International Space Station, with tons of examples. I think right now I have about 24 examples of various types of hurricanes and other types of weather phenomena that we've looked at, including some 3D images. So if you get the 3D glasses, you could actually see these storms in 3D. And I've always loved the reaction I get from meteorologists when they're able to put on a pair of glasses and look at a storm and actually be able to see the interplay at various altitudes of these clouds instead of just some flat flat cloud field, there's actually structure, and that structure helps them to decipher what is going on and where is there trouble, and where is there not trouble.
Oh my gosh. Well, it's incredibly exciting. Thank you so much for making time to be here today. We really appreciate it.
It's been my pleasure. I always enjoy talking about our work.
Absolutely. And I do want to take a moment to thank GuideForce for hosting these sessions. To learn more about GuideForce, you can visit guideforce.com. And we'll see you next time on the Tech and Space Leaders Show.